Hello, welcome to Electronics Educations. This is Vincent Chang. In this lecture, we are going to start a new series around the subject of stability of feedback. Stability of feedback. Stable, oscillation, and unstable. Explain. This is the part 1, session 1, around stability of feedback. This subject is especially difficult for most of students for two reasons. Number one, it involves the feedback structure. Number two, it involves the frequency response of a system or an amplifier. Put these two things together, make this subject very difficult for most of the students. So I'll try my best to help you understand the issue, the stability, why there's an issue, and how to tackle the issue as a designer. Ideal feedback, let's start with the ideal feedback structure. Let's say there's a signal source from the left, and then going through a mixer becomes an input signal, and penetrating through an amplifier with, again, open loop gain A becomes an output signal. Then a sample, let's sample the output signal and going backward through the feedback network and going back to the mixer. And SS minus SF becomes an SI. And then the output signal is going to deliver to the external load. This is the ideal feedback structure. Loop gain. So the definition of the loop gain is within the loop. And then you put the negative sign aside. And then you have the A times beta. A times beta is the loop gain. And then the loop gain can be treated as a signal going through A and going backward through beta, the product between the A open loop gain and the feedback factor. So two scenarios. Number one, positive loop gain. Another one is negative loop gain. So if the loop gain is positive, A beta is greater than 0, then what? Then the external sign, the negative sign, should be considered and will represent the nature, the essence of the feedback, which means, in this case, positive loop gain associated with a negative feedback, right? A negative feedback. But if the loop gain is negative, A beta is less than 0, then you have to include two negative signs. Involve two negative signs, combine these two negative signs together. The first negative sign is the external negative sign. The other one is the internal, the negativity of the loop gain. So two negative together, it becomes the positive feedback. All right? So make sure you get this, understand this. You make sure you fully understand this, okay? Sometimes it gets kind of confusing because see, the positive becomes the negative loop gain becomes the positive feedback. And then let's move on to the next issue. The next issue is the frequency response. So in this case, now let's change the pure number, the scalar, the open loop gain from a scalar form to a complex, to a transfer function. So A becomes the transfer function, and also feedback factor is also become a transfer function. So the loop gain becomes a complex quantity. So what is S? So S means the complex frequency equals the J times the angular frequency. So S, again, represents the complex frequency. The omega represents the angular frequency. All right? So it's a purely imaginary number. So now the loop gain, the product of the open loop gain becomes the product of the open loop transfer function and the feedback transfer function. All right? So open loop gain, let's maybe slow down a little bit. So open loop gain A is now becomes an open loop transfer function. And feedback factor beta now becomes a feedback transfer function. So the product, two things together, becomes a complex loop gain, L of S. the L of S. Or we can say it's the L of J omega is defined as A of J omega times beta of J omega. So when we deal with a complex quantity, when we deal with the complex number, we have to deal with two things. The first one is magnitude of the loop gain. The other one is its phase. So the magnitude and its phase. So the absolute sign represent a magnitude of the loop gain. An exponent, the theta, as function of omega. So now the magnitude becomes the function of the angular frequency, the physical frequency. And also theta also becomes a function of a physical angular frequency. So now we have to understand the frequency response of the loop gain. So let's say if we change frequency, now the magnitude will change, right? This is the magnitude response. So also if we change frequency, we increase the frequency and also the phase will change. Let's say if we have a particular specific frequency, omega subscript pi, or omega 180 degree, omega pi or omega 180 degree, which means at this frequency, the phase is exactly the same as the negative 180 degree. So the angle, make sure you get this right, all right? Okay, let me repeat that. So when we change the frequency, the phase will change, right? So let's say if we have a particular specific frequency, and at this frequency, the corresponding phase is negative 180 degree. So this frequency, we said, is denoted as omega pi, or omega 180. So why this is important? Why this is special? Of course it's important. Of course it's special. Why? Let me explain why. Let's pull up the Euler formula. The famous Euler formula. Exponential j theta equals cosine theta plus j sine theta. So if you plug in replace the angle theta with negative 180 degree, what did you get? What do you have? So cosine pi is negative 1. And sine pi is 0. So exponential, the complex term, the exponential j theta, the complex term now becomes a real number. The complex exponential term becomes a real number. What number? Negative 1. So negative 1, at this frequency, the negative 1 times the absolute quantity. So which makes the whole complex loop gain becomes a negative real number. All right? So at this, let me emphasize the importance of this. Why this matters? Because at this frequency, loop gain is negative. So which means at this frequency, loop gain is negative, which means at this frequency, the feedback becomes what? Becomes a positive. So at this frequency, the feedback becomes the positive. So it's an amplifier. But at this frequency, because of the frequency-dependent nature of the circuit, at this frequency, this amplifier, this negative feedback amplifier, turns into a positive feedback. All right? So this is the issue. 3 scenarios. At this frequency, let's focus only on this frequency, all right? Omega 180, omega pi. At this frequency, loop gain is less than 0. Let's consider 3 scenarios. You can just put down, just put down negative 1, negative 0.5, and or negative 2. So the magnitude, the absolute value, the magnitude is 1 or greater than 1 or less than 1. If it's 1, what does that mean? It means at this frequency, the circuit becomes an oscillator. At this frequency, the circuit becomes an oscillator. The circuit becomes an oscillator. Why is it an oscillator? Why it becomes an oscillator? Why is it an oscillator? Think about this. What is L? When you go through A and going, let me pull my photo up. Okay. If you go through A and going backward through beta, so how many degree involved? Is included, is introduced, 180, right? Right? Or you can say negative 180. So let me repeat that. At this frequency, if you travel, think about if you are signal, you travel through A and going through beta. So how many phase will be changed? Or how many phase will be introduced? Negative 180 degree. And then when you going around the mixer, another negative sign. So negative sign, the negativity, the negative sign represent another 180. So negative 180 plus 180 means 0 degree, means in phase. If you are a signal with the frequency of omega 180 and you travel around the loop, the phase won't change. And at this frequency, if phase won't change, if phase sustain won't change, and the magnitude of the loop gain also equals 1. So at this frequency, you can have the same magnitude doing the sustained oscillation, doing the sustained oscillation. But in the second case, what about the loop gain greater than 1? That means you travel, you're getting bigger and bigger. So it's oscillate with a growing amplitude. But if the magnitude is less than 1, then the oscillation cannot be sustained. All right? So 3 scenarios. In the first scenario, oscillation. The second scenario, the negative amplifier turns into a growing, the oscillator with a growing amplitude is unstable. The amplifier becomes an unstable. And then if the magnitude is less than 1, the amplifier circuit is stable. All right? So here's the takeaway. Number 1. Takeaway number 1, make sure you understand this. A complex loop gain and at specific frequency omega 180, omega pi, the feedback turns into a positive feedback. The structure turns into a positive feedback. Negative loop gain, positive feedback. Takeaway number 2, the second takeaway, the 3 scenario. So in order to maintain the circuit stable, in order to ensure the circuit, the amplified circuit, the feedback amplifier is stable, then at this frequency, its loop gain has to be what? At what frequency? Omega pi, omega 180. The magnitude of the loop gain has to be less than 1. Has to be less than 1. But if it equals 1, at this frequency equals 1, then oscillation happens. If greater than 1, the circuit turns into an unstable situation. So we have come to the end of the lecture. I hope you learned something very important. It's very, very important. It's the first lecture video around the subject of stability. If you found this subject is difficult, I would encourage you to watch the video again. Thanks for watching.